And so there's two types of networking of these quantum processors. I like to differentiate between a quantum networking quantum processors and a data center. So we call this cluster networking. There's a couple images on the left here showing Google and IBM and IonQ's solutions that they're planning to build. And so there you're in one data center, you likely have a lot of classical compute there too to do hybrid computation. And those are connected either through electrical connections, but there's challenges around distance and scalability and loss, and crosstalk with optical connections that'll likely be, if the transduction can be handled, it'll be much easier to do with that networking. On the right, distributed quantum computing is at longer distances. So this would be data center to data center. This is forming, you could say, the quantum internet, where you have a network of quantum devices, quantum computers across the country, could be Caltech and MIT, for example. And then you're doing this entanglement at a distance. It's likely going to look different than the cluster networking. You're going to have that delay, right? You have to transmit the photon across, hundreds or thousands of kilometers. But there'll be very unique applications that are developed for those. We're not going to focus on that networking today. You need to have a quantum repeater, which has at its core a quantum memory, which are being developed, but not yet at that production scale, to actually be able to connect, because you cannot send with high confidence a photon and have detection more than, say, 10 to 50 kilometers. Those are some of the longest experiments. So over 100 kilometers, certainly you're going to have a quantum repeater. And that is coming. There's development in that area. Mike Wood gave a talk about this last year, so you can check out that webinar. We'll focus today on those cluster networking in the same data centers.